So a nice application that we have with the net change being equal to the integral of the rate of change is with displacement and distance traveled of an object that is undergoing linear motion. So we're going to think of linear motion, straight line motion, so to speak, like a car driving down a road. We don't want to have any motion going up and down and around curves and all kinds of crazy stuff like that. So we just want linear motion. Think of a particle just on the real number line moving either left or right. So in linear motion, we're traveling at some velocity, v of t, saying feet per second, where the graph of v of t is shown here. So let's describe the object's motion. Okay. So first of all, the velocity at time 0 is 2 feet per second. Okay. What does that mean? If we're on the real number line, then it's moving to the right. If we're moving up and down, it's moving up because why? The velocity is the rate of change is positive. If the rate of change or the derivative is positive, the function's increasing, right? So we're either moving to the right, we're increasing, right, in the distance. But as time progresses, then the velocity is slowing down. In fact, by the time we get to 1 second, the velocity has gone to 0. And then what happens, velocity becomes negative. So what's happening now? Velocity is negative, rate of change is negative, then the functional function v, the original function, the position function, if you will, is now decreasing. So we're either moving to the left or going down if we're talking about straight line linear motion. And so we are velocity is negative, reaches a sort of a maximum negative at about 2.5, and then still negative, getting less negative back up to 4, and then now we're positive again, so we're moving to the right, say. So here's the problem. For an object undergoing linear motion, if we then integrate this velocity, which is the rate of change, what's going to happen? We're going to get positive area here, but what's going to happen over here where the function's below the x-axis? We're going to get negative area. And so do you see what can happen is you could integrate some positive quantity, some negative quantity, maybe after two seconds or so, then these two areas are the same. Your net change is 0. So what's that mean? Well, you've been moving to the right, right? You're moving to the right, and then at 1 second you switch and change, moving to the left. At some point you're going to be right back where you started from. Okay, and so your net change in position is 0. Your displacement is what we call that. That's the displacement. Okay, and so your displacement is just integrating that velocity function over that time interval. But the displacement could be a positive quantity, meaning you're further to the right of the object. It could be a negative quantity, meaning you're further to the right of where you started from. Or it could be negative, you're further to the left of where you started from. Or it could be 0, you're right where you started. You're right back where you started from. You moved to the right, you came back, and you're right back where you started from. Okay. But suppose I move all the way to the right some, and then come all the way back to where I started from. My displacement would be 0, but is my distance traveled 0? No, clearly I traveled all the way this way, and then all the way back, right? So that's not true. So how do we find distance traveled? Well, in that case, what will we need to do? We need the absolute value of the velocity function. You know what that's going to do to the graph here? What's that going to do? Well, if I take the absolute value, what's that graph going to look like? Well, for these portions where the velocity is positive, it's going to look the same. But where it's negative, what's going to happen? It's going to become positive, and graphically, we're going to do what? A reflection in the x-axis. Okay, and so we're going to look like that. This part will sort of flip up here. So this let me sketch a graph from here and here. So this green one, this is the absolute value of v of t. That's what this graph is here. Okay, so this looks like a W or something, right? And so now when we integrate from 1 to 4 of this function, what's going to happen? We're going to get this area above the x-axis under this curve, and it's positive. So in other words, when we're moving to the left, where the displacement vector is going to count that as negative area, and we're going to have a displacement near 0, for instance. And now we move to the right, it will accumulate positive area, and then when we move to the left, since we're taking the absolute value, that also will accumulate positive area. And so we'll get the total distance traveled. Okay, so you have to remember how to integrate absolute value functions. We did that earlier. Let's take a look at an example of this then. So a particle undergoing linear motion has this velocity in meters per second. We're going to compute the particle's displacement over the time from 0 seconds to 6 seconds. And then we're going to compute the particle's distance traveled over that same time interval. And we're going to use technology to evaluate any integrals this time. So I'm going to use that to sort of shortcut things. So let's look at part A. So what is the distance, the displacement, sorry, part A, the displacement. Well, that's just the integral over that time interval of the rate of change, which is just the velocity v of t dt. Okay. And so I'm going to get the integral from 0 to 6. So if you want practice on doing the fundamental theorem of calculus, you can. I'm going to use technology to do that. I've got the older model type calculator here. I think I showed this before. So under math, the math button right here, you have many options, and if I go down far enough, you will have the FNINT, the function integrator, I guess. And if I select that option, whichever one it is, for a lot of you, it will look like an integral, and there'll be a box where you can put the lower limit, the upper limit, and then the function itself, and then a D box. Don't forget to put the variable there. And here it's t. You can use x if you want to. In fact, I'm going to use x here. Here, the syntax is this: you put the function you're integrating first. So that would be 2, and instead of t, I'm just going to use x cubed minus 17x squared plus 30x. Right? So you put the function, comma, then you put the variable of integration. So here, it was dt. T is the variable integration. I'm going to use x in the calculator. Comma, the lower limit, which is 0, and then the comma, the upper limit, which is 6. And the comma key, again, is right above the 7 key. And then close the parentheses on that. So that's the syntax. Function integrand first, variable of integration after a comma, lower limit, upper limit. Okay. If you've got, again, the newer models, it just looks like an integral with a box for the upper and lower limit, a box for the function, and you put the and then the variable itself. So all those things you're going to put in. Okay. Now this is an approximation. However, this one does come out to be exact in this case, and you get negative 36. Okay. Now what does that mean? How would I explain this? What is the particle's displacement after 6 seconds, basically? The answer is that the displacement is 36. Our units are what? Meters per second, so our distance is in meters. What's the negative sign significance? To the left of starting position. Okay. So that negative sign there is telling me I am to the left. It's a positive sign, and I would be to the right. Okay. I'm assuming left-right motion. If you're moving up-down, then we're talking about what? 36 meters below your initial position, if it's negative. If it's positive, it's above or to the right. That many feet. So that's what the displacement means. So displacement could be positive, negative, or 0. However, when we go to distance traveled, right, what did we say that is? That's going to be the integral from 0 to 6, absolute value of v of t dt. So integral from 0 to 6, absolute value 2t cubed minus 17t squared plus 30t dt. Okay. Now, we can use the absolute value function on the calculator to do this. I want to practice, though, a little bit, and I'll show you that. I want to practice, though, how would you actually set this up without absolute value? Well, remember, we need to know about this function. Again, let me write out here 2t cubed minus 17t squared plus 30t. When is this function positive and when is it negative? In particular, when is it 0, and then we can check the intervals between and beyond those places. So if I factor this, and notice I can factor out a t first of all. That 30 there. And then can I factor this? Well, it turns out it can be factored. Obviously 2t squared, this would be 2t times t. And if we think about how to get 30, notice the product of these two is a positive number, but the sum of the outer and inner is negative, so both of these must be negative, right? Negative times negative gives me a positive. And 30, start with 5 and 6. Notice if I do negative 5 here and negative 6 here, I'll get negative 12. 6 times 2 is negative 12. Negative 5 times t is negative 5. Negative 12 and negative 5 is negative 17. Okay. And so notice this function is 0 when t is what? Either 0, 2.5, and 6. Okay. In fact, we can do a little sign check on this. So at 0, at 2.5, and at 6, we know that v of t, so this is the sign of v of t, it's 0 of those. And you just check, and if I plug in a number less than 0, like a negative number, we really, that's in this problem we're actually don't even need to. But let me just, because we're talking about from 0 to 6 here. But if I plug in a negative number, that would be negative, this would be negative, and this would be negative. So I have 3 negatives, it would be negative over here. Between 0 and 2.5, let's check a number like 1. So 1 is positive. 2 times 1 is 2 minus 5, that's negative. 1 minus 6, that's negative. Negative times positive, that's a positive. And then 2.5 to 6, like 3. If I plug in 3, I get 3 is positive. 2 times 3 is 6. 6 minus 5 is 1 positive. 3 minus 6 is negative 3. Positive times negative is negative. So remember doing that kind of sign check for a function. Okay. So what's that mean then if you really want to set this up? Then you'd have to break this integral up into these two pieces. From 0 to 2.5, since it's positive, the absolute value of the function is equal to the function. But then from 2.5 to 6, we'll add that interval. Since it's negative, what do we have to do? Remember the idea that we had to do, we had to take the absolute value, and what did that do? That negative portion did what? Got flipped up to the top. And so what's another way of flipping that up to the top? Multiplying by what? Multiplying by negative 1. So negative times t2, 2t cubed minus 17t squared plus 30t, which basically changes the sign of all those and multiplied by negative there. Okay, but there's a lot of work in evaluating these, getting the antiderivative. But let's use technology to do this, and I'm going to do it both ways. So first of all, let me do these. So let's do function. So now we're going to go from 0 to 2.5. Okay, so there's my first integral. I'm using it's the same function, right? Because I haven't changed it. But then I'm going to add to that. the other integral, which is, again, going to be negative 1 times all this. So I'm just going to distribute that negative sign. So it's going to be negative 2x cubed plus 17x squared minus 30x, right? Comma, the variable is x, comma, the lower limit is 2.5, comma, the upper limit is 6. Okay, so I've done, one integral there, from 0 to 2.5, 0 to 2.5, and then did this integral, which is the negative 1 times the original velocity function from 2.5 to 6. So add those two together, and we get the total about 85 point, we'll round up to the nearest tenth of a meter, remember meters, 85.5 meters. Just to show you, we could do this all in one estimate in the calculator. If I, let me do second entry twice, get back to this one. If I instead just go here and do this, insert, under math, you will see under NUM, right, the absolute value function, ABS. So I have to put the whole thing in parentheses, the whole function that is, right? So insert right here, close parentheses. All right, so the absolute value of all that, and still going from 0 to 6 now, right? This will also give me the same value. Takes a little bit while for it to crank through its algorithm there, but it comes up. I'll have you know, there's a slight difference there. You can tell the calculator is doing it's not doing what we're doing here. It's not finding the antiderivative and evaluating it. It's using a numerical method, numerical technique, and we'll be looking at those in depth a little bit later in the course. Okay. But again, doing it by hand, you can do it by hand just to double check your work and see. You'll find the antiderivative evaluated at these values. Quite a little bit of tedious work to do there, but you have that. Just to close, I want to show you. So by the way, notice we traveled in those 6 seconds. This total distance, 85.5 meters, is our distance traveled, but we ended up just 36 meters rather to the left of our position. And that's because why? Here's a graph of the function, right, which we say was positive from 0 to 2.5, and then from 2.5 to 6 it's negative. Well, on the first 2.5 seconds, the object starts at some position. It's moving to the right, right? And then all of a sudden, at 2.5 seconds, at that instant, 2.5 seconds, it's come to a stop, and then what? It's moving back this way. In fact, it continues to move past this, our initial position, so what? That we are, as it says, 36 meters to the left. Okay? So lots of fun, lots of neat things we can do with this idea, and so make sure you're working through the homework problems in this section.